Good day. I am presenting the paper KNN Normalized Optimization and Platform Tuning based on Hadoop. The goal is a holistic solution for a uh, big data KNN. We will show the tackling both algorithm flow and the core architecture bottleneck is necessary. Our agenda covers our agenda covers the native architecture of KNN solution and the empirical result that validation our optimize then parallelize thesis. Okay, KNN is a simple and a non-parametric classifier. A point is classified by a majority vote of its k neighbors. The inherent flow in the bottleneck. Every classification requires calculating the distance to every single point in the dataset. This brute force component must be parallelized efficiently. At the scale of big data, with millions of records and often thousands of features, this calculation becomes computationally impossible in real life. The resulting latency is too high, and simple parallelism often fails due to the architectural flow we will discuss next. We face three core constraints: computation complexity per predictions, which is too low for the large N and high D. Curse of the dimensity, Euclidean distance loses the discriminant power in the high dimension space. Third one, equal weighting. Naive KNN fails when features or neighbors are unequal. Our solution must address all three simultaneously. The old naive based implementation is an intuitive step. The map function calculates all distances and aggregate them. But the structure is fatal flawed because it uses the network inefficient as we will demonstrate. The mapper emits a pair for every training points. This results in a massive intermediate data volume shuffle across the network. OMN, where M is the test data size, N is a training set size. The volume often exceeds the input data by order of magnitude causing a crumble shuffle IO bottleneck. This design this design requires the reducer to process and sort massive globally distributed list of distances. This high cost of global aggregation and associated serialization and deserialization overhead is completely unnecessary and destroys the performance gain achieved by parallelism, the distance calculation. Our solution Our solution is the optimize then parallelize. We co-design the system. One is algorithmic optimization (KNN) for accuracy. Two, platform tuning for efficiency. This holistic strategy targets a synthetic gain where the total performance is greater than the sum of the parts. The KNN provides the mathematical rigor. The N stands for normalization and neighbor weighting. We use specific techniques to address the feature relevance and neighbor proximity, transforming the algorithm into a highly accurate classifier. To emit the curse of dimension, we use entropy weighted matrix EWM. This assigns the weighted based on the persona correlation with the class label by weighting features proportionally to the predicted power. We formally ensure that only informatic dimension contribution significantly to the distance matrix. We address equal neighbor weighting using the Gaussian kernel for the final vote. The standard deviation. uh, The standard deviation sigma is the key hyperparameter. It formally defines the radius of the influence. At distance d equals to sigma, the neighbor's weight decays to the 36.8%. This stabilizes the vote by dramatically favoring the closer neighbors. With the KNN layer complete, the algorithm is now robust and highly accurate. We have addressed all the three fundamental flaws. We now move to the crucial step, achieving the effective through architectural tuning. The goal of platform tuning is singular: eliminate the O log mn shuffle bottleneck. This is achieved by strategical levering a core Hadoop feature. We use uh, we use Hadoop Distributed Cache HDC to preload the entire training set onto the local file system on every map node. This is a crucial architectural trade-off. One-time setup cost of T in exchanging for zero network I/O during the core computational loop. The mapper is now a self-contained classifier. It accesses the local cache, performs all NKNN calculation, locally selects the k neighbors, and makes the final decision. It then only emits the final class label. This reduces the shuffle I/O volume from O log mn to linear O log m function, providing the dramatic efficiency gain. The mapper is now a self-contained classifier. It accesses all the local cache, performs all the KNN calculation, computes all NKNN distance, performs the K selection locally, makes the final classification. It then only emits the final class label. This reduces the shuffle I/O volume from O log mn to a linear manageable O mn function, which is the source of the proven 30 to 40% efficiency gain. I like to conclude that the optimized naive KNN to NKNN using Pearson entropy weighted matrix and Gaussian kernel is applied and has gained 30 to 40% of increased accuracy. And we developed a new mapped architecture that minimizes the shuffle I/O, where we have achieved a sustainable increase in both accuracy and efficiency on the Hadoop platform. The upcoming future works can be done in investigating the space complexity optimization using some special data structure. Thank you.